our summer school started in 2010. That time we also started a research center sponsored by DOE, Combustion Energy Frontier Research Center. And around that time, there's also another major center startup at Saudi Arabia, right? KAUST. And they are just doing fabulous well with this. And then one of the anchors in combustion chemistry is Professor Sarathy. And so I won't take much time, and then I'll leave the podium to Professor Sarathy.
All right,
okay.
Thanks, Ed. Yeah. And thanks, Professor Law. Okay, yeah, good morning, everybody. I think it's the first lecture I've ever been on time. Yeah, normally I have a motto, the students have to wait for me. But today I wait for the students. So I guess that's the Princeton effect, okay? So nice to be with you all. It's actually my first time teaching here in Princeton. So normally I teach in KAUST. It's a graduate university. So actually the audience is around the same. It's all master's, PhD students who are interested to learn. So I'm glad it's a similar audience today. All you guys are interested in combustion. There's still some more coming. I have some instructions from David, the videographer. He says, when you ask a question, I have to repeat it. So remind me if I don't repeat it, okay? So that the video, they can get that. So I like the topic of combustion. It's very interesting to me. I started actually only learning about combustion in my master's degree. I did my bachelor's in environmental engineering in Waterloo. And around the time of the 2000s, people were interested in alternative fuels and biofuels, and it was a hot topic. And then when I went to Toronto, I was looking for different places to do my PhD, and I went to Toronto, and there was a professor there, Murray Thompson, and he was burning biofuels in the lab. And I had no idea what burning is or combustion, but he said biofuels. I said, okay, cool, I'm going to do it. So I did my PhD in the topic of biofuels, of biodiesel and bioalcohols like butanol. And when I started my master's, I started studying this fuel called butanol. And there was an article in 2005 from British Petroleum, and it was on the front page of BBC, actually. British Petroleum said, in 5 years, we're going to make butanol commercial. Then that was 2005, and I was an excited master's student. I said, awesome, I'm going to work on butanol combustion, and in 5 years, all the vehicles on the road will be biobutanol based. Well, 5 years later, there's still no butanol vehicles, 25 years later even, on the road today. So, but still, the topic got me interested. I studied a lot about butanol, different types of alcohol fuels. You can say I'm alcoholic, even though I don't drink, but I like alcohol fuel, okay? And biodiesels, and also a lot of petroleum-derived fuels nowadays. And also, nowadays, people talk a lot about e-fuels and synthetic fuels. But in essence, they all burn the same way. Yeah, there's carbon, there's hydrogen, there's oxygen, and there's a lot of chemistry that happens between the initial reactants and the products. And that's what this course is going to be about. It's going to be about fuel chemistry and how fuels turn into heat and energy, and products that are undesirable and products that are desirable. And the principles of chemical kinetics I find very interesting because we can apply them not only to combustion, but to many other systems. I'd like to actually start always whenever we talk about kinetics. And what fascinates me about kinetics and combustion kinetics is not only that it's combustion, but that it's applied to a very complex process. And this is the words of Sir Hinshelwood, who won the Nobel Prize in chemistry for his contributions to the field of chemical kinetics, and specifically free radical-driven reactions. Hinshelwood, together with Semenov, won the Nobel Prize, and they formed the basis of pretty much everything we study today. So almost 100 years ago in the 1920s is when he made his discoveries, and then he got the Nobel Prize in 1956, and here we are in 2023 still studying and making discoveries in these concepts that he founded. So this is the words of Hinshelwood. I'll just read it out from his Nobel lecture, the beginning of his lecture. He says, nobody, I suppose, could devote many years to the study of chemical kinetics without being deeply conscious of the fascination of time and change. This is something that goes outside science into poetry. But science, subject to rigid necessity of always seeking closer approximations to the truth, itself contains many poetical elements. There are many ways in which the mysteries of chemical change might begin to impress themselves on a young chemist. And I really like this because when I started studying this field, there was the same things that got me fascinated. Time, change, this is everything that happens in a chemical reaction. And it's not science, actually. And what we'll kind of articulate throughout this course is there's no chemical mechanism or chemical model which is a definitive fact. It's all a piece of art, a masterpiece of many different chemical reactions and thermodynamic data and kinetic data, and we put it together, and we try to make sure it replicates something that's a realistic system. And that in essence, is not necessarily a true science, okay? Of course, we've got to apply the fundamentals of thermodynamics, kinetics, transport theory, but in the end, we bring it all together in something that's a piece of art. And that's what I think. Chemical kinetic models are works of art. And some people make very beautiful works of art. Some of them, are not so good, okay? And the idea, I want you all to start to try to understand, how do you make these works of art? How do you make them more beautiful? And apply them to very complex systems. And we'll talk more about complex systems, okay? And why we want to study these complex systems. So in the next 5 days or so, we'll go over different aspects. We'll start pretty basic today, okay? We'll try to review some basic aspects of thermochemistry, kinetics, and transport, but also to put this all like in a historical perspective of how this field of chemical kinetics evolved in the last 100 years. And it started, in the early 1900s, and a lot of discoveries made through experiments in the 1920s, 1930s, and then nowadays with modern computers, after 1970s, 1980s, we started building larger and larger models and try to also articulate a future for chemical kinetics, which maybe have much more parallels with artificial intelligence and machine learning. We will try to cover what is needed for a good chemical kinetic model. How do you generate the thermodynamic data accurately? How do you develop chemical kinetic data, either using simple models or quantum chemistry? We will also even discuss things like applications of machine learning to improve the development or accelerate the development of chemical kinetic models. Similarly, we'll do that for transport data using different types of quantitative structure property relationships. We'll talk about experiments. How many people here are experimentalists? Okay, so half the room is experimentalist. The rest are theoreticians or modelers? Yeah, and how many are both? They have to do both because their advisor doesn't like them, okay? Or couldn't afford 2 different students, okay? So sometimes you do both. So we'll talk about different types of data for acquiring kinetic data, specific things like basic thermochemistry data, kinetic data, but also data that can be used for validation of kinetic models, which the combustion community widely uses. And then we'll also look at how we can combine all these things in simulations of reactors and compare them against experimental data. But maybe around the 3rd day, around Wednesday, we'll actually start building a chemical kinetic model together, a very comprehensive one. And that's sometimes I say the best way to learn is, just do it, okay? And we will do that together. We'll talk about high temperature reactions, low temperature reactions for a prototypical hydrocarbon, and we'll develop the model together. We'll show how we can write out all the reactions, where can we get the thermal data, the transport data, the kinetic data. We'll look at how we can validate that against different experiments like jet-stirred reactors and flow reactors and shock tubes and so on. And then we'll also talk a bit about how this whole aspect of chemical kinetics and combustion is relevant to other fields like atmospheric chemistry, or catalysis, or even human metabolism, biology. Because it's all, in the end, it's all the same principles. Just a matter of different types of physics happening in the presence of a catalyst or an enzyme, or in the atmosphere, things happen at lower temperature than in a combustion system. But essentially, similar types of reactions are proceeding. And we'll try at the end to even bring the aspect of very complex systems when you try to simulate combustion for a real fuel in a turbine or an engine, you're dealing with something that's extremely complex, a hydrocarbon fuel or a biofuel with many different components inside of it, and that makes the chemistry significantly more complex. Okay, there's a few books we're going to use. Okay, the couple of books, first one is Batin, Leclerc, Simi, and Blue Rock. Again, you don't have to have these books, but it's useful for you for future reference if you ever want to go to a text and find a lot of different information about this field. These are a couple of books. So the book by Batin, Leclerc came out about 10 years ago. It's in Springer. It's called Cleaner Combustion. And the second one is by Bob Key, Coltrane and Glaborg, an older book, I think, from the 1990s on chemically reacting flow, theory and practice. And this is the first cleaner combustion. I don't know if you can see the different chapters there, but it's about chapters about development of detailed chemical kinetic models, automatic mechanism generation tools, multi-step models for different types of hydrocarbons and biomass, and then also has things on experimental methods and even model reduction. So it's a reasonably good book as a reference for you to look in the future if you're interested to go further into this field. And then the second one is from Bob Key, Professor Key. You must all know Chemkin, and he was one of the authors of Chemkin, the initial codes that was written in Sandia National Labs in the early 80s. And then he went on to become a professor in Colorado School of Mines, where he still is today. But Key wrote this very nice book called Chemically Reacting Flow Theory and Practice. And it's much more than not about chemistry, but about how you model, take chemical kinetic models, thermodynamic data, transport data, and how you model real systems. Things like flow reactors, perfectly stirred reactors, counterflow flames, one-dimensional counterflow flames, pre-mixed flames, and so on. And yeah, I think these two books together give you a good overview of how you develop kinetic models and then how you actually apply them to simulate combustion-related systems. Okay, so this is another quote, okay, from Samuel Carlin. And he says, the purpose of models is not to fit the data, but to sharpen the questions. And I want you to think about that, okay, for a couple of seconds. And he's a statistician, okay? He develops statistical models. And he always said, when you develop these models, you shouldn't build a model just to fit experimental data or observed data. You should build these models to refine the questions that you're asking. And this is exactly what we want to do in chemical kinetic modeling. If there's anything, when we talk about all these different inputs that go into reaction mechanisms, and we build the models, if you think we're trying to come to a definitive answer and trying to fit a lot of experimental data and say my model is the best because it fits the data, well, that's not the objective, okay? The objective is to use these models to understand more about an extremely complicated system. A system with a fuel, which is extremely complex, undergoing a combustion process in a system that's extremely complex, and try to understand more about that system so you can design it better, maybe improve its efficiency, reduce its emissions, and so on. And if we're just trying to build models to fit data, well, I think you can see we can now do that pretty well with artificial intelligence and machine learning. But what do you learn from this? Yeah, if you can't interrogate the model, understand what are its limitations, what are the limitations of the system to which you apply the model, you're not going to be able to design a better system. So we want to build models, but we want to build these models which will help us to understand basic questions of extremely complex systems. And the complex systems are complex for multiple reasons, okay? So one, if we talk about combustion systems, engines, turbines, boilers, maybe some of you are studying plasma reactors, any type of thermochemical reactor, they're extremely complex because the conditions in which they're operating encounter many different conditions in which the physics of the system and the chemistry of the system changes significantly. So here we have a simple 4-stroke reciprocating internal combustion engine. You introduce your fuel. Well, first of all, the fuel is never one component, or rarely one component. Maybe if it's hydrogen in the future, that's going to be easy because there's only one component. But today, the fuels that we put into engines are extremely complex. Hundreds of components, sometimes thousands of components. And we'll talk more about the complexity of fuels because that determines then the complexity of the models. Once this fuel and oxidizer are inducted into the chamber, because of the reciprocating motion inside of the piston chamber, you have a change in temperature. As temperature increases, different types of chemical reactions will be activated, and that leads to additional complexity. Some chemical reactions will even be deactivated as the temperature increases, and we'll talk about that, those physics as well. In addition, as temperature rises, it's happening because the pressure is rising. Many of the chemical reactions in the models are pressure dependent. The kinetics of the reaction can change as a function of pressure, and we'll talk about that as well. Depending on the speed of the engine, an engine, we characterize the speed based on the RPM, the rotations per minute. If you're operating an engine around 1600 RPM, one crank angle, so 1 degree motion of the engine is about 1/4 of a millisecond. So, and that changes throughout your engine operating cycle. You're going anywhere from 1,000 RPM to 8,000 RPM. So sometimes the residence times are extremely short. And this determines then things like the ignition delay time, the anti-knock, or the anti-knock quality of your fuel, which is to prevent the knocking in the end gas. So residence time is highly varying depending on the engine speed and load. And then the mixture fraction, of course. So we are always changing. Typically in older engines, we used to keep a fixed mixture fraction. You would typically want to operate your SI engine near stoichiometric, maybe slightly lean if you want to mitigate the NOx emissions, and your diesel engines would be globally quite lean, so phi of 0.2 to 0.3. But nowadays, you have very complex engines. Take, for example, the SkyActiv engine. That's they say spark-assisted compression ignition. Nobody really knows what's happening inside, but it's some kind of mixed mode combustion process. So it's not always operating like a traditional SI engine where you have a spark igniting a premix flame. Sometimes they inject the fuel a bit early, so you get a partially premixed mixture. So it operates somewhat partially premixed homogeneous combustion, and then you fire your spark to control the timing. And that mixture fraction can change depending on the load. So at low load, they might operate a bit richer, maybe 0.6, 0.7 equivalence ratio. But then at high load, they want to go very lean to mitigate the NOx emissions. So modern engines are extremely complex. You go to a gas turbine, you might operate very lean to mitigate NOx emissions when you're taking off. But then once you get to cruising altitude, you can lower the amount of fuel that's going into the chamber, and you can get lower emissions and more steady state combustion processes. So every engine, highly varying because of the operating conditions and the fuel. But regardless of how complex it is, you can understand things using the fundamental principles of chemical kinetics or reaction engineering. These are understanding the transport processes. So at a molecular level, the transport processes that are important are diffusion. So at the flame front, what governs the chemical reaction scale is the diffusion processes between molecules. You'll hear in the afternoon from Professor Heinz Pitch about fluid mechanics, turbulence. This is all to govern the global mixing processes and various aspects of how fuel and oxidizer and emissions are mixed inside of a combustion chamber. But at the chemical front, which is the flame, everything is governed by diffusion, okay? So diffusion transport is something we model from a chemical kinetic perspective. The other bulk fluid mechanic properties, of course, we need to use Newton's equations for that. And then we have thermodynamics. So the heats of formation, the entropies, the Gibbs free energies, the heat capacity, these are which govern the temporal change of temperature and energy in the system, and also determine which reactions are important at different conditions. And then, of course, the kinetics. So the kinetic parameters for each individual reaction, which will determine how the fuel and oxidizer behave in this changing environment. And these are all things we will try to understand, first at a high level, but then in a more practical level, detailed level, by actually building a model for a fuel that will go into an engine. So this is our process for chemical kinetic modeling. I borrow this, this kind of roadmap from Professor Dr. Pitts from Lawrence Livermore National Laboratories. It kind of articulates from a very fundamental level, how do we start building the chemical kinetic models, and how does it take us to the end of actually understanding how how pollutants or efficiency of an engine is optimized. Let me see if the pointer works. Do you see it up there? Yeah. So at the very beginning, one can say every chemical reaction that happens is an elementary chemical reaction. So we can, in principle, determine the kinetics of that reaction from quantum chemistry or ab initio calculations by solving the Schrödinger's equation. Now, these calculations are not easy to do, okay? They're extremely time-consuming, computationally expensive, and require a great level of expertise from a theoretical chemist to conduct properly. But nevertheless, one could start with ab initio calculations. We can calculate from ab initio calculations. If we know the stationary point energy, or the 0-point energy for your reactant, say one molecule methane reacting with OH radical. If you know that energy of those two molecules, the energy of the transition state, the transition state which governs the activation energy of the reaction, and you know the energy of the products, then in principle, yes, you can calculate using statistical thermodynamics and transition state theory the kinetic parameters for your reaction. Doing that in practice is very challenging because calculating these energies is extremely time-consuming. Performing the transition state theory calculations, there are many different ways you can do it, and sometimes you make a lot of approximations. Today, the state of the art from some of the best computational chemists like Dr. Stephen Klippenstein or Professor Donald Trular, they'll say they can get you to rate constants which are about a factor of 2 or 3 from real measurements across a broad temperature range. And that's using the state of the art today, so you get a factor of 2 or 3. If you go to somebody like Charlie Westbrook or Henry Curran, they say they can guess the rate within a factor of 2 or 3 as well. So that's the computational chemist or the theoretician and the artist. Both of them should make these approximations. Some use it using a lot of computers. Others do it based on a lot of experience for many different types of reactions of similar, you can say similar configuration, and they can approximate rates. So in the end, we're not at the point where we can actually predict or calculate a rate within, say, 5% or 10% of a real value. And that's going to be a long ways away because simply the calculations that need to be performed are far too complicated. You can also calculate your thermodynamic data from quantum chemical calculations. You can calculate the minimum energy path for your reaction path, which will be used to calculate the kinetics. So one, in principle, could do this for all the reactions in your mechanism. Then you can build a complex reaction mechanism. It can have 50 species, 100 species, sometimes thousands of species. And you can build these reaction mechanisms with thermal data and start to simulate real fuels. Oftentimes, for something like hydrogen and oxygen or methane, we can have a subset of these reactions actually calculated from first principles. But if we go to a jet fuel or a diesel or a gasoline, there's thousands of species. We can hardly calculate the kinetic parameters for a few dozens. So we make a lot of estimations using rules. We'll talk about reaction rate rules because in practice, this is what we have to do to build chemical kinetic models for real fuels. Then we build the models. We validate them against different types of experiments. Some of you might be doing these experiments, like flow reactor experiments, jet-stirred reactor, rapid compression machines, shock tubes, different types of flames. And we'll talk about all those experiments as well. And then we validate our models against these experiments. You can oftentimes take these models, reduce them in size, and then apply them to an engine. And many of us do engine experiments. Well, in an engine, you can never apply a detailed chemical kinetic model because the fluid mechanics are so complex. If you need to solve the chemistry in every single cell in your CFD domain, sometimes it's hundreds of thousands of cells or millions of cells. Yeah, again, the computational power does not afford that yet. So we oftentimes take a very detailed model with thousands of reactions and tens of thousands of species, and we bring it down to 50 species or 100 species and several hundred reactions, which can be utilized in a CFD model. Okay, so this is the overall approach that we want to apply, and we want to apply it to real fuels. Real fuels are things like gasoline, diesel, jet fuel, biomass, biofuels, mixtures of these different fuels. And sometimes these fuels will come from different resources, right? You can get fuel from petroleum, you can get fuel from biomass, you can get fuel using CO2 and hydrogen and make an e-fuel. But today, the most complicated fuels are the ones that are coming still from petroleum. And that's what this chart shows. Okay, and just to give you an idea, when we get crude oil from the refinery, crude oil from the field, it's brought to a refinery. The first process inside of the refinery is a very simple distillation, a crude distillation, and that's what we show here. And when we do this distillation process, we fraction the fuel, a crude oil, into different hydrocarbon fractions. And the complexity of that mixture depends pretty much on the boiling point. So at the top of this distillation column, you have the very lightest gases coming off, like methane, ethane, propane. These are typically bottled as gases. You can buy methane probably for your gas stove at home, or you have liquid petroleum gas, LPG, propane for your barbecues. So these fuels are bottled, and they're very low carbon number, anywhere from 1 carbon atom, CH4, up to 3 or 4 carbon atoms. If you go to butane, C4H10, 4 carbon atoms. And let me see if this, again, very simply, we can. So 3 of the lightest fuels. I don't write the hydrogens, okay? Most of the time I won't write the hydrogens. I'll just write the carbon molecules. If I draw a line, it's connected to a hydrogen. So methane, ethane, propane, yeah? These are your 3 simplest hydrocarbon fuels. And the interesting part is they're very low carbon number, but they're not complex because also there's no isomers of any of these molecules, right? The first isomer we only have is when we come to butane. You have N-butane and isobutane, okay? So it's the first hydrocarbon with some isomers. Yeah. And every one of these isomers is going to react differently, because the nature of the carbon-hydrogen bonds is what governs the reactivity of the mixture, and we'll see why that is and how we build the models. So when we build models for methane, ethane, propane, relatively less complexity, because First of all, we know all the bonds, we know all the structures. Once we come to butane and higher hydrocarbons, for every single carbon chain, we have multiple isomers. So for butane, you have N-butane, isobutane. For pentane, you have N-pentane, isopentane, and neopentane. For hexane, again, now you have multiple, more and more isomers that are possible. Apologies, for propane, you can also have cyclopropane. You can have a cyclic isomer, but okay, it's not very much found in any real fuels, yeah, because it's energetically very unstable. The first stable cyclic hydrocarbon is typically cyclopentane, C5. Cyclopentane, cyclohexane, those are the main ones. And then, of course, you can go to aromatic hydrocarbons. So less complexity at the lighter end. And for that reason, we have many chemical kinetic models. You have kinetic models from probably the 1970s. As soon as computers were starting to be utilized, people started building models for methane. So the first ones were from, there's a very famous paper, 1983, by Westbrook and Dreyer. Dreyer was a very famous professor from Princeton University, and Charlie Westbrook from Lawrence Livermore National Lab. These are the guys who kind of pioneered modern chemical kinetics for use in computer applications. Yeah? And of course, it had a guy from Livermore, Dr. Westbrook, because they had the access to the biggest computers in the world at the time. Yeah, and Professor Dreyer here at Princeton was a good collaborator of Charlie Westbrook, and they built these models. And the paper was titled Detailed Chemical Kinetic Models of Methane and Methanol, so CH3OH. So the first, the lowest oxygenated fuel, methanol, and methane. And that was actually a very nice paper. If you have some time, go read it. It's the first one that described very detailed reaction mechanisms. And nowadays, yeah, every year, people are writing papers about methane, methanol, ethane, and there's, I'm going to say hundreds, if not thousands of kinetic models for things like these light hydrocarbons. You can even go lighter, CO, carbon monoxide, they call C1 model for carbon monoxide. Carbon monoxide burns, right? If you take carbon monoxide, mix it with oxygen in the presence of water, you'll form CO2. So yeah, carbon monoxide can burn, and of course hydrogen can burn as well. Hydrogen, many kinetic models, it's the foundation of every kinetic model that we use. So we'll talk about those in more detail. But from a real fuel complexity, we start with the hydrocarbons. Now you come to the middle range, the first liquids. So the lightest liquid, I think butane becomes liquid in the winter time in your gasoline. So butane can be in winter gas here in New Jersey or New York when it's around freezing outside. They'll put some butane dissolved about 5% in your gasoline. Then when it comes into the gasoline, into the engine is warm, maybe at the beginning, 35, 40 degrees Celsius as the engine starts up. The butane volatilizes, and that allows the first starting of the engine. So, but most of the gasoline fuels in Saudi Arabia, we don't put butane in the gas because it's too hot outside. At 40 degrees C, it'll just vaporize. In summer gasoline here in New York, or now today it's really hot these days, they don't put butane in the gasoline. So they start at pentane and hexane. So different formulations for different seasons, different parts of the world. That adds complexity to gas. There's no one type of gasoline. Okay, gasoline changes in different states throughout the year, in different countries throughout the world. So we start around, say, C4, but maybe C5, C6, and we go up to about C10. And the mixtures then have many more isomers, simple as that. So you have things like heptane, different isomers of heptane, C7, isooctane, many isomers of octane, and then you start having aromatics like a bit of benzene, but mostly xylene and toluene, and that makes up your middle fraction. And here again, kinetic models, now we're down from thousands, maybe to a few dozen good ones, okay, out there. And then you come to jet fuels, a bit heavier. So gasoline was about C5 to C10 at the highest. Jet fuel starts around C9, 9 carbon atoms, goes to about C14 at the top end. So this is kerosene. Again, kerosene will vary depending on the region, depending on the engine requirements in that region. So then kerosene, again, more isomers, you're now on the C10, but now you get rid of your aromatics, typically around C10 or C11, and now you have mainly straight chain hydrocarbons. So alkanes, linear alkanes, branched alkanes, but many more different isomers of those hydrocarbons. And then diesel starts at the low end around C9, because they want the light hydrocarbons in, and then it goes on the heavy end up to about C18, C19. So again, much more complexity in diesel fuel. And now you're talking about very few kinetic models that are actually reliable. And the most complex are things actually nobody even wants to touch. It's like fuel oil. Anybody, where do we use fuel oil today? Somebody said it, louder. Ships. Yeah, so marine fuel oil, marine gas oil, all your big container ships going around the world are burning what we call bunker fuel, which is nasty, nasty stuff, okay? It's the bottom of the barrel, so to speak. After the crude oil is you take off all the good stuff, they leave the crap, and then they use that for ships. Why? Well, ships, nobody really cares about the emissions, right? Because it's out in the ocean. If you watch Titanic and you see all that stuff, well, that was coal-fired ship anyway, steam engines. But the modern engines are internal combustion engines. Yeah, nasty stuff coming out. And those fuels are really complex. We started about 8-9 years ago building models for marine fuel oil. This stuff is, now we're not, the minimum carbon number is like C25, but then it goes up to like C100, and your average carbon is like C50 to C60. And this is stuff like, okay, if you put it on the table here, it's a solid. So they got to heat it up to about 200 degrees C to get it flowing, and then they could put that into the engine. So really complex, of course, the carbon numbers are very high, but then once you come to this bottom of the barrel, they also have sulfur in there. So then you have carbon, hydrogen, and sulfur. And then many more isomers possible once you bring sulfur into the picture as well. So, and nowadays, because of climate change, because of emissions, we have new mandates coming on board for ships. So there's something called IMO 2020, International Maritime Organization 2020, which says that the fuel that you use in a ship has to now be below, I think, 0.5% sulfur, 0.5% sulfur. Traditionally, these fuels have about 3.5% sulfur. So you get a lot of SO2 emissions. Again, if it's operating in the open ocean, nobody cares. But when it comes into port at a city, LA, New York, wherever you have your big ports, Rotterdam, Jeddah, there's a lot of SO2 emissions that in the port. So they said, okay, no more fuel oil, or no more high sulfur fuel oil allowed in ships. Well, it's a problem because there's no such thing as low sulfur fuel oil. All fuel oil has high sulfur. And if you take the sulfur out, you got diesel. So now the problem is everybody's just burning diesel to comply with the regulations. Or they burn fuel oil and they pay the penalty, because it's more affordable today to pay the penalty than actually get a low sulfur fuel. So more complexity, and we'll even talk then probably towards the end, Thursday or Friday, about how we actually model like these very nasty heavy fuels. And that's just petroleum, right? So biofuels, on the other hand, are relatively easier in my opinion. Yeah? If you said butanol or ethanol, it's only one fuel. Yeah, biodiesel is a mixture of about maybe 12 to 14 different fatty acids, methyl esters, less complicated. Synthetic fuels like e-fuels. So actually your future is easier than mine, okay? If we get rid of all petroleum, like combustion kinetics will be relatively easier because the number of hydrocarbons or fuel mixtures that you need to model are different. Of course, we have things like ammonia coming, and ammonia is a bit complicated. It seems easy, yeah, ammonia combustion kinetics, but it's actually quite complicated. So again, same principles will be used though to solve those problems. So here at the heavy end, not many kinetic models. Maybe if we're lucky, we'll stop using these fuels so we don't have to build the kinetic models anymore, yeah. And again, and because of this complexity in real fuels, the approach we use is to make a surrogate, okay? You cannot model the combustion kinetics of gasoline, 250, 300 different components, diesel, 500 to 700 components, heavy fuel oil, 1,000, maybe 2,000 different components, impossible. You can't build models for all these things. So what we do today, because again, we're limited in the number of kinetic modelers and the types of models we can build and the computational power, we use a surrogate. So a surrogate is a representative mixture of hydrocarbons which replicate some of the overall important aspects of your real fuel. And surrogate modeling is maybe only about 15, 20 years old. So the time of Westbrook and Dreyer, methanol, methane, up until about the 1980s, up until about the early 2000s, people were only modeling pure hydrocarbons. Actually, the first famous paper on the first surrogate was by Henry Curran on the combustion kinetics of N-heptane and isooctane. Why N-heptane, isooctane? Anybody know? Gasoline, what is it for gasoline? Yeah, it's your PRF surrogate, right? Primary reference fuel surrogate. It's a surrogate, okay? It's actually not even a fuel, but we'll talk about that after, okay? N-heptane, C7H16, isooctane, yeah. So this was the first surrogate, okay, let's say, PRF's primary reference fuel. The paper, I think, 1997 by Henry Curran, Charlie Westbrook, Bill Pitts, yeah? So, and I say it's not even a fuel because it's a primary reference fuel. It's not even a fuel we use in any vehicle today, right? This is a mixture that's used in CFR engines to determine the octane number of fuels. So it was the first gasoline-relevant fuel, let's say. But is it relevant for real gasoline? Well, not necessarily, because real gasoline has aromatics. It doesn't only have C7 and C8. It has C5 and C6 and C9. And it has cycloalkanes. So a better surrogate nowadays might have more components. So you might have N-heptane to represent the medium carbon length and N-butane to represent the lighter fractions. You might have some branched alkanes as well, like isopentane, 2-methyl-hexane, 2 branches, so 2,5-dimethyl hexane, an isomer, a different isomer of octane. Isooctane, this one is what we call 2,2,4. Yeah. Isooctane is not even the right name. We should write the exact name, 2,2,4 trimethylpentane. Yeah. So 2,2,4 trimethylpentane is not even found in real gasoline. It's very actually hard to get isooctane from a refinery mixture. So that's a very obscure molecule we use in primary reference field for determining octane. But if you measure the detailed hydrocarbon analysis of a real gasoline, you'll find very little isooctane actually there, or 2,2,4 trimethylpentane. You'll find more of these kind of dimethylated alkanes. They're more common. Okay, and then you might have some different olefins and cycloalkanes. So cyclohexane, cyclopentane, which I mentioned. These can be up to about 20% of your mixture. Hexene, some olefins, and some aromatics. Yeah, so aromatics like toluene and trimethylbenzene. And this is just representative. You could pick different components. It doesn't have to be these components. But then you build models for each of these individual components. You blend them together, and you have a kinetic model for your mixture. But again, we still have to build the models for each of these components. Hence, the approach in the end becomes the same. But complexity is there because we need to do more and more of these models if we want to better represent the real fuel. So for gasoline, we might have 7, 8, 9 components. Diesel, it's even harder because, again, more carbon number range, more different types of hydrocarbons, you need more components. One thing to note here, I might use some words interchangeably. We use, in chemical engineering, don't ask me why, in oil and gas industry, they use something called PIONA, okay? PIONA is to describe the different types of hydrocarbons. The P is for paraffins. And this is, in chemistry, we say N-alkanes, right? So when I say paraffin, I'm talking about N-alkanes. Isoparaffins is isoalkanes. O is, anybody know? Olefin is also an alkene, right? Is alkenes. So anything with a double bond, we call it olefin or alkene. N, where does this name come from? I have no idea. Okay, naphthene. But they say that's a cycloalkane, so a cyclic hydrocarbon without any double bonds. And then the last one is aromatic. Aromatic is the same, aromatic. So PIONA so oftentimes when you talk about real fuels, we look at the PIONA distribution. So it's the N-alkanes, isoalkanes, alkenes, cycloalkanes, and aromatics. But again, most of the stuff we look at in real fuels, like gasoline, diesel, is mainly N-alkane, isoalkane, and some aromatics. Cycloalkane, people did not pay much attention to until the last, say, 15 years, because about 80% of your fuel is these three. And N-alkanes, isoalkanes pretty much govern your octane number, yeah, which is important in gasoline fuels. Your ignition delay time in diesel engines, your cetane number is governed mainly by these. And why people care about aromatics? Soot. Yeah, most of your soot or your PAH formation is coming from the aromatic. So people paid less attention to these. Olefin is typically only, anyways, regulated in gasoline to about 5% at the most. And some European specs, they allow more. But I think here in US, I think level 3 gasoline is maximum 5% by volume. And naphthenes, well, you want them. They're very good antinol quality, good energy density, doesn't make soot. But the refiners want to pull it out because it has much more value in other chemical applications than putting it into fuels. So you typically have less cycloalkanes. Okay, so this is a real fuel, what it would look like. So before we stop, we will ask a question, okay, to you guys. And I want you to maybe discuss amongst yourselves for a couple of minutes. If you were to make your own fuel, what would it look like, okay? And what do you think is important characteristic for that fuel to have? And if you could make that, how would you design it? So first thing, what do you want a fuel to have? Should it react with oxygen? What should be the major products from oxidation? What should be the energy density? What should be the phase, a liquid, a gas? What do you think? So what do you think are the key properties of a fuel that you would want to have? You guys talk about it, okay? And actually, I'll let you talk, for 5-6 minutes. Then we'll talk as a team, and then we'll break out for the break. So take a few minutes to talk to your neighbor about this. Write me some key properties of a fuel that you want to have. All right. Okay, let's see what you guys say. Okay. So what did you all think? What were some of the things you discussed for the best fuel, or your ideal fuel?
We said that we probably don't want a toxic product.
Okay.
That's probably an important thing.
Okay, so they don't want a fuel without a toxic product. Okay. That's the most important thing.
One of them.
One of them. Yeah. Okay. Anything else? Any other key features you found? Huh? Energy density. Yeah. Okay, like what? What would be a good energy density? Okay. Anybody have a number? What they think is reasonable? Okay, what is that fuel? Yeah, so most of your hydrocarbons like jet fuel, diesel fuel, gasoline, they're around there, 39 to 42. We'll see that later, those values from the lower heating value. Yeah, that's pretty good for automotive fuel. We did fuel design for Formula One, for McLaren, and they want the maximum energy density because in the vehicle, at the time we were doing the design, you were only allowed to fill the car with 105 kilos of fuel. So that's part of the formula. So they say 105 kilos for the whole race. Yeah, no refilling. They used to allow refueling until around 2010. One of the cars lit on fire or something, and they said, okay, during the refueling at the pit stop. So they said, no more refueling. The car gets 105 kilos, and then you want energy density. And so the fuels which have the highest energy density are alkanes, yeah, alkanes. Once you put a double bond in there, like an aromatic, you lose out. Your energy density drops to around 39. The highest are alkanes, 42. So on average, you come to about 41, 40, because there's always a mixture. Megajoules per kilogram, right? Or megajoules per liter. It's a bit different if you go to liters because of the density. Okay, then I said there, 10 kilojoules or 8 megajoules, that's pretty low. Yeah. But there's some fuels that we use which are lower. What is a typical fuel which has a lower energy density? Yeah? Okay. On a liter basis, volumetric it's low, but on mass it's quite high. What is it on mass basis? 120? Yeah, it's around 120, right? Per kilogram, so very high. But it's a gas, so on a volumetric it's very low. So, but liquid fuel, that's similar to gasoline in terms of it's a liquid, like we have ethanol, methanol, ethanol, they're much lower. Because you put oxygen in there, it doesn't provide any heating value, but it takes up space, takes up weight. I don't know ethanol on the top of my head. I think, 28, 29? Methanol is a bit around there, 226. Okay, so yeah, you said energy density is important. You think it's not important, like, I know I talk a lot to the guys like in ConocoPhillips and Shell and Chevron. There's one of my colleagues works in Chevron. And I said, why don't you put more alcohol in your fuel? You know, it's actually, alcohols are very good. Low emissions, toxicity of the products is pretty low because you make less aromatics. Burn pretty well. High octane. You can get better efficiency. But in the end, he said, nobody wants to buy fuel with alcohols, with ethanol or methanol, because the energy density is too low. Nobody wants to, you got to go fill up your car twice as much. And in the end, the price is actually not that much different on a volumetric basis. Nobody wants to buy the fuel. And they've done all kinds of tests in California, in Texas. So customers don't buy fuels with high alcohol content. They want the good stuff, yeah? All right, so yeah, energy density, very important. Anybody else? Yeah? Okay, safe to store and transport, good one. Okay, you gotta make it at a low cost. So hydrogen is great, very little emission, very high energy density, but pretty hard to produce, right? And pretty hard to transport and store. And that's why we don't have a lot of it today. Yeah? You can actually make pretty good engines that run on hydrogen. But yeah, because of those reasons, we don't have a wide ammonia, yeah. Coming back to their point, is ammonia a good one? Toxicity? Well, it's toxic as a fuel, and then it's toxic if you don't burn all the fuel, right? So the major problem with ammonia is ammonia slip. You don't burn all the fuel, some of that ammonia left over in the exhaust. That's bad news, yeah? And that's a challenge in ammonia combustion. And then also you make other things like other emissions, NOxes and N2O. But also the fuel I think you can store it. and easier than hydrogen to store and transport, right? But harder to burn than hydrogen. Anybody else? What did you guys think in the back there? Yeah. Oh, good. Methanol with tetraethyl lead. Why? Good fun. Yeah. Have you tried it?
Yes.
Yeah. I don't know. It's pretty hard to buy tetraethyl lead these days. I've tried. And you got to import it like from South Africa, and the paperwork is a bit shady. Yeah. And why did you say that? Besides fun.
No,
Yeah.
and it's that's both the research octane and wood octane. Very good for
Tetraethyl lead
yes.
in methanol. Yeah. How much lead did you add?
I don't remember. I mean, it's
Okay.
120 plus.
Yeah, I think it's a pretty good fuel, pretty good anti-knock additive, tetraethyl lead. So there was a chemical engineer I think he's ExxonMobil, Kettering, Charles Kettering. Charles Kettering is about the 1930s. He is the one who started using a CFR engine to determine the octane scale of hydrocarbon fuels. And I think he was around Pennsylvania. ExxonMobil was in this part of the world when they started. First refineries started coming up in Pennsylvania. And they were distilling the fractions, and they were trying to understand which ones are the best for spark ignition engines. And Kettering came up with this, this scale of, okay, we have a CFR engine. We can measure the octane number of a fuel by comparing it against some reference fuels. So he took a reference mixture of a reference fuel of heptane and isooctane. So the low end is N-heptane 0. The high end is isooctane 100. And then he found there were some fuels that they were outside the scale. They had a better anti-knock property than isooctane. So things like methanol and toluene. So to extend the scale, he found this compound tetraethyl lead. Yeah? And he said this molecule, and I think the octane number of like pure tetraethyl lead is like 800 or something. Because you put like a few milligrams in a liter of fuel, and it boosts the octane number by crazy. So if you look at the octane number, the CFR octane number ASTM standard, it says if a fuel is more than isooctane, you start adding a bit of tetraethyl lead to measure the octane number. And there's some correlation for that. And he found that, it's a great anti-knock improver. And then the businessmen in ExxonMobil said, fantastic. Kettering, you've discovered, and I think he patented tetraethyl lead, this molecule, which is a super octane additive. And they started using it in commercial gasoline. Yeah? And it was used for many years until, I'm going to say the 70s, until which time it was banned. Well, Kettering was a very good chemist, a scientist in a lab, and he said, this is a fantastic molecule, but he said, it's extremely toxic. And he said, never use this in motor gasoline for commercial applications because it's extremely toxic. It's going to contaminate the water supply. It's going to get in people's system because it's also assimilated very well into the human body. And he wrote papers after he discovered it, after he issued the patent, why to never use it. Well, they shut him up and they fired him. And ExxonMobil said, no, we're going to use it. It's a fantastic molecule. And then they used it widely, and then until the 1970s or so, it was widely used, at which time doctors started to see children having lead in their systems, lead toxicity, water aquifers contaminated with lead, at which time it was banned. Yeah? And then also, it was the time of the three-way catalytic converter. The three-way catalytic converter gets contaminated by lead. So they couldn't use it anymore, even in very small quantities, because it would damage the catalytic converter. So lead is great. Still used in motor applications, still some motorsports, but still hard to get. And so now most of the time, even in Formula One, they don't allow this stuff. They try to stay away from it. Okay. So toxicity, yeah. Energy density, fun. What's a fun fuel is a good one. Anything else? What did you guys say? Anything different? Yeah. Okay. Okay, so now some properties of the fuel, like the ignition delay time, which is governed by chemical kinetics. Actually, all these things have some chemical kinetic relevance as well, like the toxicity, the energy density, the ignition delay times. Yeah. What about the first one? Does it have to react with oxygen? Sorry, go ahead.
Yeah, I think the first one is very important, react with the oxygen.
Okay.
Already, pay a lot for the fuel, and I guess they do not want to pay more for the oxidizer.
Okay. So you want it to react with oxygen in the air, right?
Yes, because air is cheap or even free to everywhere.
Okay, air is free, yeah. Does it have to react with oxygen, a fuel?
No.
No? What did you say? What do you say?
React with nitrogen.
Huh?
More of it, let it react with nitrogen.
Oh, you want it to react with nitrogen?
Sure.
Well, that's harder. Yeah. But, I mean, nitrogen, I'm trying to think of a fuel that reacts with nitrogen. I mean, you need some electronegative compound. It doesn't have to be oxygen. Typically, even chlorine, yeah, or, huh? Fluorine, chlorine, iodine, yes? Huh? No? Yeah, fluorine, bromine. Yeah, you could have energetic systems, which are fuels that are not burning with oxygen. They burn with other electronegative element, yeah? Of course, you don't have them widely available. We want oxygen because it's everywhere, right? It's in the air. Well, the problem with oxygen in the air is you make CO2, but that CO2 is a nitrogen. So then you cannot remove that CO2. Actually, the bad part about combustion is not that it makes CO2. It's that CO2 is diluted in nitrogen, and you can't take it out and put it anywhere, right? Because 79% nitrogen in the air. At the end of combustion, you have about 75% nitrogen still around. It didn't go anywhere. And that CO2 is super hard to separate. And I guess later this week, Professor Herzog, who's like a world leader in carbon capture, he's going to articulate this problem. So I actually say CO2 is not a combustion problem, okay? It's a problem of separation and removal and making sure it doesn't go back into the air, the atmosphere. So if you burn in pure oxygen, you can have pure CO2. It would be easy to capture. So if every car had a fuel and then a tank of pure oxygen, you could have pure CO2 coming out the end and water and put that back in the tank that had the oxygen. But again, nobody wants to carry oxygen. It's super heavy and hard to store. So I wrote a paper once on a fuel which I thought was the best one, okay? And it was a US combustion meeting in Pasadena. I think it was like 2018. So I said the best fuel was performic acid, okay? And it looks like this. Like that, performic acid. And okay, I was just having fun with it. And why did I say it? And I built a chemical kinetic model and, to describe how this fuel burns. Well, I said the same thing. I want a fuel that has a reasonably good energy density, but this one actually is pretty bad because there's too much oxygen in there. It's like 6 megajoules per kilogram, so it's actually below the minimum. But the thing is, when this fuel starts reacting, you don't need any oxygen. It has all the oxygen it needs inside of the fuel, yeah? So, and when it burns, you break this bond, you get OH, then you break this bond, and this OH reacts with the thing, and then you get CO2 and water. So when performic acid burns, it only makes CO2 and water, and it doesn't need any oxygen from the air. It has all the oxygen it needs. So, okay, then you could just, the products are CO2 and water. You can store them in the vehicle and use them later. You can also make this fuel from CO2 and water. You need hydrogen peroxide and formic acid to make performic acid. So I had some fun with it, okay. It never made it outside of the US combustion meeting because it was a bit of a joke. But it works, okay? And I built a kinetic model. It has a good ignition delay time. It's actually, you can prevent it from reacting if you manage it right. The problem is, if you don't store it correctly, it's way too reactive, okay? And I said to my students, I built a model, and I said, hey, look, this looks really good. Now go do the experiment. Well, nobody wanted to do the experiment with this fuel. Because the problem is, you have a little bit of heat, like 80 degrees C, and boom, it blows up right away, okay? It's super dangerous. So the students never wanted to work with it. And okay, when we did the safety analysis, yeah, it wasn't worth it. And there was a story of one professor had a student in University of McGill University. Performic acid, you can buy it. It's a mixture of 50% water, 50% performic acid. And then it's stable when it's in water. So, but I said, you need a pure fuel. And this professor in McGill wanted pure performic acid. So he told his student, go to the lab and distill out the water, okay? And he started distilling out the water, and it was like 60% performic acid, 70%. When he reached 80% performic acid, the whole thing blew up in his face. And then the professor got fired for blowing up his student. So good fuels, but not enough students to work on them, okay? So you guys take a break. Maybe 15 minutes or so, we'll come back.